a major source of water and power for millions of people out west, but an ongoing drought has caused the lake to fall to record low levels.
The West, as you know, is in the grip of a mega drought, and Lake Mead in particular, this is near Las Vegas, is showing the dramatic effect of falling water levels.
Cracks have begun to emerge beneath Lake Mead, the largest reservoir in the United States, alarming scientists and geologists alike. Once a beacon of 20th century engineering and water security, Lake Mead now finds itself at the epicenter of a deepening crisis. The sudden appearance of fissures along its lakebed and surrounding terrain is not just a startling geological development, it could signal a potentially catastrophic shift in the structural integrity of the region. As scientists scramble to investigate the causes, what's unfolding beneath the surface of Lake Mead is raising urgent questions about natural stability, regional sustainability, and the long-term viability of human infrastructure built around assumptions that may no longer hold. Before we start, smash the like and subscribe buttons for more updates. The cracks didn't begin with a loud bang or tremor. Instead, they revealed themselves slowly, as subtle lines that snaked across the dry, receding edges of the lake, in areas where the water had long pulled back due to prolonged drought and overuse. At first glance, these cracks might have seemed like typical evidence of drying earth, shrinking, breaking apart from heat and dehydration. But deeper analysis has shown that these are not mere surface-level symptoms. They extend downward and outward, cutting across geological layers and forming patterns that suggest shifting stress in the very ground supporting the basin. These aren't ordinary stress fractures. They hint at tectonic movement, subterranean collapse zones, or changes in underground water pressure dynamics. For a region already teetering from water shortages and environmental strain, this discovery injects a new level of unpredictability. Lake Mead has been losing water for years, largely due to prolonged drought fueled by climate change, combined with unrelenting demand from agriculture, urban development, and industry. As water levels dropped, vast sections of the lakebed were exposed for the first time in decades. It was on this newly revealed landscape that the fractures began to appear in earnest. Geological teams initially noted these changes during routine topographical surveys. At first, they suspected surface desiccation, but further investigation using ground-penetrating radar and seismic reflection technology revealed that the cracks reached far deeper than expected. Some cut through layers of sedimentary rock, while others reached into the harder bedrock below, an ominous sign that subsurface stressors are in play. The implications of these cracks extend well beyond aesthetic or scientific curiosity. Lake Mead is not only a critical reservoir that supplies water to over 25 million people across the Southwest, it also forms part of a delicate balance of geological and hydrological systems. If the foundation beneath the lake is shifting, it could affect the integrity of the Hoover Dam, a critical structure that has stood for nearly a century. Though the dam itself has not yet shown signs of instability, the evolving geology beneath Lake Mead raises questions about how long it can continue to do so without recalibration or reinforcement. Cracks in the earth hint at pressure buildups or voids developing underground, precursors in some cases to sinkholes or even seismic events. More troubling is what these cracks might say about the broader geological pressures building in the region. The western United States is a complex patchwork of tectonic plates, fault lines, and volcanic systems. While Lake Mead is not directly atop a major fault line like the San Andreas, it sits within a network of geological structures that respond to stress across the wider area. The weight of the lake's water once applied a stabilizing force on the underlying crust. Now, as that water diminishes, the crust may be rebounding, a process known as isostatic rebound. This phenomenon can lead to the uplift of land, increased seismic activity, and destabilization of the surrounding terrain. In essence, the earth beneath Lake Mead is adjusting to a rapidly changing burden, and the cracks could be the surface expression of this deeper tectonic unease. The growing web of fissures is not uniform. In some areas they are narrow and shallow, but in others they gape wide, with measurable displacement on either side. Some have created step-like faults, where one section of earth has dropped relative to the other. These features are eerily similar to those seen in areas preparing for landslides or subsidence. If enough material shifts beneath the reservoir, it could trigger localized collapses, sending tons of sediment slumping into the remaining water. Such an event might not only affect water quality but also disrupt ecosystems already pushed to the brink. Moreover, if subsurface cavities are forming, as some preliminary models suggest, then even greater shifts may be yet to come. In addition to geological instability, the cracks raise alarm bells about infrastructure embedded in and around the lakebed. Lake Mead is surrounded by intake towers, pumping stations, pipes, and tunnels, all designed to extract and channel water from the reservoir to cities like Las Vegas, Phoenix, and Los Angeles. Many of these systems were designed decades ago, with little consideration for the kind of foundational instability now emerging. If the ground beneath these structures continues to shift, the risk of collapse or failure increases. A rupture in one of the intake tunnels, for instance, could compromise water delivery to millions of people in a region where water scarcity is already critical. The long-term impact of such failures would be enormous, not only in terms of economic disruption, but also in triggering water wars across an already contested landscape. Beneath the surface, where the eyes can't easily reach, hydrogeologists are also raising concerns about what's happening to the aquifers that sit below and adjacent to Lake Mead. The receding lake has already altered groundwater gradients, causing shifts in flow directions and pressure levels. If these cracks are creating new pathways, then the hydrology of the entire region could be undergoing a fundamental transformation. Contaminants trapped in sediment could be mobilized, leaching into freshwater zones and rendering them unsafe. Saltwater intrusion, a danger in many stressed basins, could become a real possibility. Even if water were to return to the lake in the future, the conditions for clean, reliable water storage might be permanently changed. The psychological impact of these developments cannot be overlooked. For decades, Lake Mead has stood as a symbol of American ingenuity, an engineered marvel that turned arid land into fertile ground for millions. Its gradual decline, already demoralizing to those who depend on it, now takes on a more unsettling tone. Cracks in the lakebed become metaphors for deeper societal fractures. The over-reliance on finite resources, the slow-motion consequences of climate inertia, and the hubris of believing nature can be permanently subdued by technology. The fact that the very ground beneath the reservoir is breaking apart underscores the limits of control. It is not just a lake drying up, it is a foundation giving way. As scientists continue to map and model the evolving cracks, questions multiply. Could the fractures connect to deeper fault systems previously unmapped? Are there signs of impending seismic activity? Should engineering teams begin reinforcing critical infrastructure now, or wait for clearer data? How does one prepare a region of tens of millions for geological changes that may unfold slowly, but carry irreversible consequences? These are not questions with easy answers, but they demand immediate attention. Compounding the urgency is the fact that these changes are occurring in a region already plagued by extreme heat, wildfires, and shifting rainfall patterns. The environmental systems surrounding Lake Mead are finely tuned to the availability of water. Birds, fish, insects, and plants all exist in precarious balance, often depending on thin slivers of wetland, creek, or riparian zone. If the ground beneath them is changing, collapsing, draining, shifting, these ecosystems could experience sudden collapse. Endangered species could lose what little habitat remains. Restoration efforts, already underfunded and overwhelmed, would have to contend not just with a lack of water, but with instability in the very soil they aim to recover. Technological monitoring has now become essential. Satellite imaging, LiDAR scans, and seismic sensors are being deployed to track the evolution of the cracks. Algorithms trained to detect minute changes in surface topology are parsing through mountains of data, flagging areas of rapid displacement or deformation. In one area north of Boulder Beach, satellite imagery revealed a 7-centimeter downward shift in terrain over just a 2-month period, a staggering rate of movement in geological terms. This is not a slow-motion disaster developing over centuries. It is unfolding in real time, with each week bringing new, potentially destabilizing developments. While there is no conclusive evidence yet that these cracks will lead to a large-scale geological event, the scientific community is on high alert. History offers sobering precedents. Other large reservoirs, such as China's Zipingpu Dam, have been linked to seismic events following changes in water load. The phenomenon, known as reservoir-induced seismicity, suggests that human-made lakes are not passive actors, they can interact with Earth's crust in complex and unpredictable ways. If similar forces are now at work beneath Lake Mead, the American Southwest could be entering uncharted territory. Lake Mead's status as a keystone of the Colorado River system further amplifies the stakes. The river, stretched thin across 7 U.S. states and parts of Mexico, depends on Mead as a storage hub, regulating flow and ensuring equitable distribution. If the structural integrity of Lake Mead is compromised, the entire system could be thrown into chaos. Contingency plans exist, but none fully account for foundational shifts in the Earth itself. What was once seen as a stable backdrop, a fixed landscape upon which policy and planning could be based, now reveals itself as an active, shifting terrain. Water management in the West must now contend not just with political and hydrological uncertainty, but with geological unpredictability. Communities that live near Lake Mead, or rely on its water, are beginning to grasp the seriousness of what's unfolding. Local farmers, already pressed by dwindling allocations and rising costs, fear that disruptions in delivery could wipe out harvests or permanently damage their operations. Municipal planners in cities like Las Vegas must now think not only about conservation, but also about the potential for structural failure. Insurance companies, faced with rising claims and uncertain risk projections, are reevaluating coverage policies for infrastructure and property in the region. The question hanging over all of this is chillingly simple. What happens if the cracks keep spreading? If subsidence accelerates, if new fissures open in critical zones, or if seismic activity is triggered by these underlying stresses, the region could face a cascading series of events. Dams, pipelines, bridges, and roads may become unstable. Emergency services would be stretched thin. Migration away from the area could begin, not out of panic, but as a rational response to growing uncertainty. It's a scenario no one wants to imagine, yet one that must now be actively considered. Even without a dramatic geological event, the slow deterioration of the lakebed presents a grinding threat. It undermines confidence, complicates planning, and creates a background hum of anxiety that affects every decision made around water use, land development, and sustainability. The era of assuming that Lake Mead would remain a static, reliable fixture is over. The land is shifting, the earth is speaking, and its message is far from comforting. The cracks beneath Lake Mead are more than geological anomalies. They are warnings etched in the ground, lines drawn by a planet reacting to decades of strain, imbalance, and neglect. They force a confrontation not only with physical instability, but with the mindset that created it. As scientists delve deeper into the ground and into the data, the imperative is not just to understand what is happening, but to reckon with what it means. While the discovery of cracks beneath Lake Mead is deeply concerning in itself, the broader implications ripple far beyond the lake's immediate vicinity. As researchers pivot from identifying the cracks to interpreting their deeper meanings, new layers of complexity continue to emerge. The geophysical dynamics beneath Lake Mead are part of a much larger regional puzzle, one involving subterranean stress, water depletion, structural vulnerability, and climatic extremities working in concert. The desert Southwest, already stretched thin from decades of overdevelopment and warming temperatures, may now be entering a phase of geological reawakening, triggered not by external seismic events, but by the slow, grinding collapse of its own overburdened resources. Beneath the surface of the reservoir lies a complex network of geological strata that have been subjected to millennia of compression, uplift, and sedimentation. When Hoover Dam was constructed and Lake Mead began to fill in the 1930s, billions of tons of water added immense pressure to the crust beneath the newly formed lake. For decades, this weight suppressed minor shifts in the bedrock, acting almost like a natural tamping mechanism that held certain tectonic forces in check. Now, as that water recedes and the pressure is lifted, those forces are no longer constrained. This unburdening of the crust is not merely a reversal of past conditions. It introduces entirely new stress regimes that can reactivate dormant fault lines or trigger faults that were previously unknown. One of the more disconcerting hypotheses gaining traction among geophysicists is the potential for what's known as fault reactivation. Faults, even inactive ones, often lie just beneath the surface, hidden within sedimentary basins or embedded within bedrock. These faults are sensitive to changes in pore pressure, the pressure of fluids in the spaces between rock grains. As the lake shrinks, it's not just the water that disappears. The hydraulic pressure that once seeped into the underlying rock and helped stabilize fault planes diminishes as well. Without that pressure to lubricate the fault boundaries and reduce friction, stress accumulates and the likelihood of slippage increases. The sudden reawakening of these buried faults could lead to a series of low to moderate earthquakes. Or worse, an unexpected rupture that catches the region completely off guard. Adding further complexity is the behavior of the subterranean water table. Aquifers that once enjoyed equilibrium with the full reservoir are now desynchronizing, creating voids in some regions and surges in others. Some aquifers are experiencing downward recharge as cracks form new vertical conduits, allowing water to seep to levels where it had not reached for centuries. Others are draining rapidly, especially in areas where human extraction from groundwater sources has intensified in response to falling reservoir levels. These uneven hydrodynamic movements don't just reshape the subsurface water architecture, they also destabilize the rock formations that those aquifers pass through. In regions where over-extraction has caused the water table to drop significantly, the surrounding material begins to compact, leading to subsidence that, when combined with emerging cracks, accelerates the transformation of the terrain from solid to semi-collapsible. To understand the gravity of this development, it's crucial to consider the human landscape constructed around the reliability of Lake Mead. The entire southwestern United States has been engineered to function on the assumption that this man-made lake will continue to operate as a giant, predictable water bank. Cities, suburbs, farms, highways, and power grids, all these infrastructures are interconnected and dependent on stable ground. As fissures open in what was once considered immovable earth, the logic of permanence begins to erode. Urban planning, zoning, and long-term development schemes that once extended confidently decades into the future are now being reassessed under the looming uncertainty of geophysical change. Engineers responsible for maintaining water intake systems from the lake are confronting a daunting set of new challenges. Cracks near intake structures not only threaten to destabilize these facilities physically, they may also allow sediment and debris to infiltrate water conduits. Over time, this can lead to clogging, corrosion, or mechanical failure of pumps and filtration units. In an arid region where every gallon counts, even a minor disruption to water delivery systems could translate into widespread shortages. Moreover, the necessity to relocate or redesign these intake points in response to both dropping water levels and shifting ground is a logistical and financial nightmare. Retrofitting infrastructure embedded into a changing geological surface demands a level of adaptive engineering that has rarely been tested on such a scale. One emerging point of focus is the interaction between the cracked lakebed and potential gas emissions. Crustal shifts and fractures in deep sediment layers may open pathways for trapped gases, such as methane, carbon dioxide, or radon, to migrate upward. Though the lake itself isn't sitting atop a known gas reservoir, subterranean organic material long buried under pressure may begin to decompose and release gases through newly opened cracks. In extreme cases, gas emissions from lake beds have led to explosive events, such as those recorded in volcanic crater lakes in Africa. While the geology of Lake Mead is vastly different, even small-scale gas releases could pose health hazards or ignite in the presence of equipment or dry vegetation nearby. In tandem with physical geological changes, the ecology of the lake is undergoing severe stress. Fish populations, already declining due to warming waters and reduced oxygen levels, may be affected by the sediment disturbance caused by shifting ground. Fissures that breach the lake bottom can stir up ancient layers of sediment, some of which contain heavy metals, toxins, or pollutants deposited decades ago when environmental regulations were more lenient. The reintroduction of these materials into the water column could poison aquatic life and taint water supplies for human use. Algal blooms, which thrive in warm, nutrient-rich disturbed waters, could increase in frequency and severity, leading to further ecological degradation. Crucially, these cracks and the uncertainty they bring are altering the discourse around climate adaptation. Much of the planning for climate resilience has focused on mitigating heat, reducing emissions, and improving water efficiency. Now, with the Earth itself destabilizing under the weight of cumulative pressures, adaptation must expand to include the possibility of rapid geological transformation. Emergency preparedness plans must begin to account not just for fires and floods, but for earth movement, infrastructure collapse, and even the forced abandonment of certain regions. The financial and insurance sectors are also beginning to grapple with the implications of a fractured Lake Mead basin. Properties near the lake, once prized for their views and recreational access, may see values plummet if fears of land instability grow. Insurance companies, wary of the unpredictability that comes with geological upheaval, may raise premiums or pull coverage altogether in high-risk zones. The ripple effects could be felt throughout local economies, triggering property abandonment, municipal revenue shortfalls, and increased pressure on social services as affected populations seek new places to live and work. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on cracks opening beneath Lake Mead right now? We want to hear from you. Thank you for watching, and see you next time.